I would have addressed it in the last slide, but it's more germane to say now. So why are we doing all of this? As we have seen, we have a very clean algorithm via Gale-Shapley, which we've known from the 60s and so on, right, that gives us a stable matching. So why do we want a geometric perspective? I mean, is it just to make our life hard? No, because as I said yesterday, there are exponential, for any arbitrary instance, there could be exponential number of stable matchings. Gale-Shapley gives us the two extremes, the man optimal or the woman optimal. Suppose we want to find something, a stable matching which has additional properties, such as you saw in during Pallavi's lecture, egalitarian stable matching. It's a stable matching with an additional property, right? This sort of a polytope description is a very it's understood to be a very simple description, because you see it has polynomial number of variables, polynomial in xij's, right, the number of edges, that many number of variables. It has polynomial number of constraints, number of men, women, like 2n, and this for the pairs and so on, right, polynomial number of constraints. And a stable matching is any matching that will assignment to these values, to these variables xij, that satisfies all these constraints. Now, to capture egalitarian stable matching, all I have to do is add an objective minimization objective function that basically tells me what the egalitarian cost of the matching x will be. And then using this, I will be able to solve that problem also in polynomial time. Okay? So, there are, as you know, that in a generally there can be n factorial number of matching solutions, right, in a sort of an arbitrary bipartite graph and so on, I mean balanced bipartite graph. Sometimes we want something more than just any solution. Then having a polytope description, one that is this clean and where the extremal points are so well characterized, allows us to capture those otherwise elusive solutions. Min cost, Kavita was given an example of min cost perfect matching, is perhaps the most basic optimization question we can ask in the realm of perfect matching. I want a perfect matching, but there are edge costs and I want to minimize the cost, right. So, that sort of thing is why we study this kind of mathematical formulation. Okay. Was this a question that any of you were wondering, that why are we even doing this when we have Gale-Shapley, which we have known for so long? Why are people wasting their time doing all of this? Okay. Another thing, nobody pointed this out, but I just want you to notice this, which is that when I was talking about, okay, first and foremost, this, the first statement is, it is a 0-1 integral solution, okay, the normal fraction, normal stable matching solution. The relaxation of that is something like this when written in the linear constraint form, where xij need not necessarily be 0 or 1, but some non-negative value which can't be more than this thing. Okay. Now, notice I did not write at most 1, because this automatically takes care of it, right. Nothing, no variable will be assigned to 1 because of this constraint. Okay. Now, so all that is fine. So, that is why it is a relaxation. I fractionalize the constraint and allow the integers to sort of take fractional value. This blocking pair, which I am calling number 5, is different from the blocking pair condition I stated before. That was greater than equal to 1, but I claim that is equivalent to this constraint. Okay. Can you tell me why? If you see, if you pay close attention to how the summation is happening, you will see. Yeah, so from the man's perspective M, right, we know that this constraint holds. So, xmw plus the summation of all his partners whom he likes strictly better than w, plus the summation of the x values of all those partners he likes strictly worse than w, all add up to 1. Here in the blocking that previous constraint, I was considering only those women whom M likes strictly more than W. Here I am doing the opposite. I am considering all those women. So, if I adjust this value here, this and this value, I am going to get that that value back, the women that he likes strictly more than W. So, this is basically an equivalent way of saying what we of capturing the blocking pair condition. Okay. One thing to note here is a particular problem can have very many different LP formulations. Sometimes working with one is easier or better or gives better result than other. That happens. Okay. So, sometimes somebody will come up with a set of constraints, and then for subsequent researchers will try to tighten the constraint, try to study that as much as possible, and if they see a limit, like there is some sort of problem they want to solve and they cannot, then they oftentimes the next step is to redefine, come up with different set of constraints that capture, that are equivalent in the sense that they do exactly the same or something more. Okay, so that is something that happens fairly often. Now, I hope this is the only slide where this thing happened, this weird stuff. Okay, so now this is the sort of, this was a very significant result when it came out. This was given by T.O. Sethuraman in 1998. Yeah, wonderful paper really. So, it says that this PSM, the stable matching polytope, is the convex hull of all the stable matching solutions. So, the stable matching solutions taken, by stable matching solution I mean assignments to those variable xij's taken together may not give rise to a convex set, but this polytope, right, captures the convex, the smallest convex set that contains all those solutions. Okay. All right. So, we will see a really nice geometric proof of this. Okay. So, I hope if you do not understand anything, please ask me, I will stop and explain. So, let us start by considering a feasible solution in the, okay, to show that something is a convex hull, what do we have to show?
Just there is a condition that the linear combination of all the points, the set of points.
Yes, you knew this.
The coefficient sum is equals to 1.
Yes, that basically is the definition of a convex hull, right. I did not have that on this thing. So, basically what we want to say is we want to write it as a linear composition of the solutions, yes, of the set of points, and those constants, the multiplicative constant, coefficient, they will add up to 1. That is the correct definition of showing this. Okay. So, that is the type of thing that we are getting to. Now, suppose we start with x as a feasible solution in the stable matching polytope. Okay. We will show that x can be written as a convex combination of the stable matchings. These are the integral stable matchings. Okay. Now, this is a result that I will not be proving. It uses a bit of the primal dual sort of complementary slackness condition which you saw earlier today. But let us skip it, let us assume that this is true. Let us understand what this means and then we will just sort of use it. Okay. So, what this means is for any feasible solution in the polytope, if the value xij is greater than 0, then this constraint is tight. Here we are using the stable matching, the second blocking pair constraint, okay, not the first one. See, look at the indexing here, I am looking from I's perspective, looking at all those women that I like strictly less than j. And also from this man woman j's perspective, I am looking at all those men that she likes strictly less than I. Okay. So, this is that second modified constraint that is tight. Okay. Okay, let us come back to the, okay. Now for every man mi, I will consider these values xij. So, for man mi, there are these n values, right, xi1, xi2, xi3, xi, and for every woman there is an xi value, correct. So, if an xij value is non-zero, I consider an interval of that much length in the 0, 1, in the real line 0 to 1. Because of this whole thing, you can see if xij is 0, all the other intervals corresponding to this man I, they will all add up to 1. Okay? So, sorry, it is not this constraint, it is the matching constraint. I am so sorry, this is not about the man I, this is man and as well as the woman. This thing, we have this constraint, right, that the summation of the xij values will equal to 1 for any fixed I. So, for the man I, it is like he can be fractionally assigned to up until capacity 1. Because of this, I can think of the entire interval 0 to 1 real line being broken into these segments, where each segment corresponds to whatever the length of xij is. Okay? So, I will show a picture. Now, these intervals are placed on the line 0, 1 real line in the increasing order, in the decreasing order of the men's preference. And I do the exact same thing from the women's perspective. For each woman wj, I create n intervals of length xij for each of the man I index from 1 to n, and because it all adds up to 1, I can think of the entire 0, 1 line being broken into these sub intervals. Okay? But when I arrange the intervals corresponding to the women, I do it in the opposite order of the men. If this is decreasing, that should be increasing. If this is increasing, that should be decreasing. Okay, so here I think it is taking decreasing. Okay. So now it looks something like this. These are all 0 to 1 real line. Okay. For each man and each woman, I have such a line stacked on one top of the other. Okay. So, and this xij is saying how much is this man mi paired or matched with this woman j. I have arranged these segments. So, for man I, the first segment is say xi1, xi2, xi3. I sort them and arrange it in the decreasing order. So, the one that comes first is the one that has the highest preference in mi's preference ranking. Okay? I do this. Similarly, I do the same thing for the women, but in the opposite direction. Okay? Now, notice something, if this is an interval xij which is non-zero, the way I have arranged them, it means that all those people who come to the left of this interval belong to women, or are talking about the fractional assignment of man I to women who are strictly more preferred than j, correct? And on this side you have all the summation of those xi values corresponding to all the women who are preferred more than okay, this is from the women's side. Okay, this from the man's perspective, these are the people who he likes more than j, and these are the women he likes less than j. Now, I do the same thing from the women's side. Is there some property that you can see following that lemma that we just now used? What should this imply now? See, there is an interval xij on the man's mi's row. There is also an interval corresponding to xij in the women wj's row. Okay? Because of this quantity, I should annotate. Because we are saying that if xij is non-zero, so this is not one single, there is some length associated with this, this quantity is equal to 1. What is this quantity? This quantity says xij plus all those women that I likes less than j. So, who are those? They are these people, right? This quantity corresponds to this squiggly line, right? What is this quantity? These are all those women, all those men, right, sorry, men that j likes less than I. So, they are these things. right? This portion in the women J is this thing, this part and this part, they all add up to 1. So, this portion must correspond to this area, correct? Because this is a 0, 1 line, right? This blue part, this is this blue part and this is the squiggly part is taken over, this portion already covers it. So, what is left is this much. So, quantity wise, this quantity should be equal to this. Agreed? This is just line stacking, okay. So, what this means? Yes, so what does this mean? Remember, from the women's perspective, our arrangement was such that whoever is on this side, they are liked less by the women, right. So, this portion here, this segment here is actually the Xij segment, but from the women J's row. Got it? So, it has to be that Xij interval that comes from the women J, from the woman J's row corresponds, like completely overlaps the Xij interval from the man Mi's row. Okay. So, now we will use this quite significantly in creating an assignment, okay, a fractional kind of assignment. Okay. Now, I generate a random variable, a random value between 0 and 1. It can't be 0, it cannot exceed 1. Okay. All right. So, it is somewhere, all right. This is just for notation, just to see that it has to lie in some interval and so on and so forth. As such, you need not be in Xij, it can be somewhere else also. Now, this is how I create the assignment. If U actually falls, so I look at every man, every row that I have here. From the man Mi's perspective, I see where is U, this uniformly at random generated value. If it falls in the interval, let us say Xik, and that, so it means that that interval has to be part of a non-zero interval, right. If the interval itself is 0, the point does not lie on that. So, if wherever the point lies, it falls in some non-zero interval, non-zero segment. That tells me it indicates a woman with whom he has non-zero fractional matching. I then assign that woman to this man. Okay? I do the same thing from the women's side when I am looking at the row corresponding to the woman. There is only one U, it falls up, if it is here, it intersects everybody's segment that falls within this dotted portion, right. So, depending on what segment falls here and for which man, I get an assignment for this man, for this woman. For these women here, I see what is this interval, who is this interval corresponding to, that tells me who should this man be assigned to. That is what leads me to this assignment. Now, the question is, this is some function I have defined. Is it clear to you why this should be a matching? Sorry?
It falls in only one interval for a man, and if it is in the ijth interval for man I, then for woman j it falls in the same ijth interval.
Correct, exactly. That property, because of this coinciding property, right, if you assigned Mi, if U falls in this interval, Mi will get assigned to woman j, and well, because of the coincidence property, woman j will be assigned to Mi. Right. So, at least this assignment is well defined, like people are agreeing that they are matched to each other. Why can't I have a situation where one man gets assigned to 2 women, or 2 women gets assigned to 1 man, or any of these conditions? Well, because u only falls in one interval. Exactly, it's a one point and it falls in exactly one segment in every row, right. So, that's at least tells us that, well, this is a complete, this type of assignment is a matching in like this sort of sense. Okay. It's okay so far? So, now we will try to show that this is actually a stable matching. Why is it a stable matching? Okay, rather from what we just now discussed, that everybody gets assigned to exactly one woman, the man and women are the same thing. So, it is basically a perfect matching, it is not just a matching, it is a perfect matching, right. Everybody gets somebody, because from every row I will find what the segment is and everybody gets some partner. Okay. So, so the next thing to prove would be why is it a stable matching? Why is it a stable matching? The diagram basically gives the argument. A little louder.
Is it because the way we arranged it for men it was decreasing, the other way around?
Yes, but can you tell me exactly why? So, let us take a pair M and W and see what happens, right. Let us take, suppose it is a blocking pair M W, right. The M and W prefer each other to whoever they are assigned to currently. No, that is the most obvious way to prove anything in stable. So, suppose that Mi prefers Wk to his partner in this assignment Wj. So, this is I kept it with Wj because this is the thing. U is here in Xij, U also falls in this interval. So, because Mi prefers Wk more than this woman Wi, right. So, it must be that the interval that this woman, this K woman must appear to the left of this woman J, right, somewhere here, correct. Let me write Wk here. Now, but what can we say from Wk's perspective? This is Wk here. We know, so this is the Xik interval, right. Okay, I already had. Again, due to the coincidence property, when I go to the row of the woman K, Wk, the same Xik will lie here. The same whatever is here, same Xik is here, correct. But we know U is on the exact same position in the real line, right, but U is to the right of Xik. So, what does that mean? That this woman Wk's partner must be in this interval, whichever interval contains this U point is her current partner, and clearly the way we have arranged the segments, she prefers this guy over I, therefore it can't be a blocking pair. Is it clear? I do not think there has ever been a cuter proof of such. Usually this blocking pair stable matching thing can be so tedious, you are like checking who is preferring whom. This is so nice, right, highly non-trivial I would say. I do not know how one would come up with an idea as nice as this. Okay. So, basically what we have is a stable matching where everybody is matched. So, this sort of a random sampling thing has at least allowed us to find a matching. Notice this matching is randomized, this assignment, this solution X is randomized because it heavily depends on this probabilistic event of where U falls, correct? Okay. All right. Sorry, what? I forget that the board is not symmetric on both sides. So, let us call this assignment that we have obtained as XU. Why we are talking about U? Because if the random sampling was gave a different outcome, the assignment would change. Okay? So, we are subscripting with U, where we say XU ij is 1 if and only if man Mi is assigned to Wj. So, you should see that this is basically a random variable. It depends on U and u affects who I gets matched to, correct? All right. So now, can you see why this should be true? Why the expectation of the variable x u I j should be, okay, this is basically probability, this thing, uniform probability, a continuous probability, this thing, this y x u I j. Okay, let's talk about why is this, why does this take the this form, this expectation? Because x u I j is a 0 1 variable, right? If you are assigned, if the u falls in the interval x I j, x u I j takes value 1, 0 otherwise. So, the expectation of this value is literally the probability that the value u falls in the interval x I j. Okay? The probability that u falls in the value x I j is equal to the length of x I j. Length of x I j is literally this x I j value, right? There is lot of abuse of notation, but I can keep saying interval of x I j, and so it just loads up the terminology. Okay. Now what? So, notice x u as an assignment is composed of these random variables I and j's, like this, in this sort of indicator random variable whether I is matched to j or not. So, if I tallied up all the pairs of I and j, I would get back x u. Okay? So, if I look at this value, it is basically just integrating over the entire range, which was 0 to 1, and this indicator value. Okay. So, this allows us to write x u as a combination, x as a combination of this x u values as u varies on the interval 0 and 1. This may be not that easy to visualize, but this is what the math at least tells, right? Okay. So, now we are almost, now how many segments or intervals did we create? There were 2 n rows for the n men and n rows for the n women. Each of the rows had how many segments? At most n non-zero segments, right? So, overall you have order n square possibilities, correct? Okay. So, this x u can have at most this many number of distinct assignments, really based on in which of the segments u falls, right? Okay. So, this basically says that we have created a convex combination of x u over the interval 0 1. Like the fact that they all add up, that coefficients add up to 0, add up to 1 follows from the fact that the entire thing is arranged on the real line 0 to 1. So, basically almost we killed multiple birds with one stone, just the way we stacked the intervals, and we got this blocking pair non-blocking pair property as well as the convex combination. Everything sort of follows from the way the intervals were arranged. Okay. All right. So this basically shows that the polytope, the PSM, is the convex hull of the stable matching solutions. So, the first consequence of this is that now, okay, so this was the thing that we wanted to do, right? That we want, so explicitly speaking, how would we do this? So this is basically a recipe. Now, X be a feasible fractional solution in the SM polytope. We do it as we did it in this theorem. Now, you basically sort the coordinates of the endpoints from in increasing order, okay, and you arrange them. So, each row has n plus 1 distinct coordinates, and overall across 2n rows you would have, this is exactly the argument we said before, and the endpoints would be, this is the leftmost interval is 0 and the rightmost interval has the endpoint 1, right, because we are covering the 0 1 line. I'm going to drop something. Now, for each random number, so as we saw, u falls in one of these intervals, right. So, falling in one of these interval means that you are on the leftmost you are the leftmost endpoint and the rightmost endpoints coincide with the rightmost endpoint of the previous interval and the leftmost endpoint of the next interval. So that's what this is. Maybe I should draw it. So I drew that picture yesterday late night and then I sort of lost the energy to draw more pictures. But these things are better explained like this. Okay, so this is I1, I2, let's say I3. So if U falls here, U is basically ensconced between the rightmost endpoint of this interval and the leftmost endpoint of the next interval. That's what this means. So I basically, this is like say this each interval is basically getting identified by its two endpoints, and therefore you can say that U lies in between a sort of segment such as this. Okay. Now let this thing be the integral stable matching solution obtained with this value. So suppose U fell on this endpoint precisely, and that's the stable matching solution we obtained. Then this is basically a telegraphic type of a series and so on and so forth. If you just expand this, you will see that X can be written in this form. It's just basic algebra. It just can be, okay, just trust it. So therefore, what have we done? We took these fractional solutions, each of these are the fractional solutions, and expressed X in terms of that. And obviously these endpoints, these values, these coefficients are between 0, 1 because they lie between 0 and 1, so the difference can't be more than 1, right, and they all add up to 1. So the coefficient, so this basically gives me the gives me this thing that I can express every fractional solution in terms of the integral solutions. So the main point to note here is that the integral solutions are obtained when something falls right on the end point of an interval, and every intermediate in between point can be written as a sort of a linear combination of those solutions that would have been right on the end point of the intervals. That's what this is. Okay. Now, this is perhaps the most interesting property. So I knew this theorem long before I knew the proof of that, the one that I just now showed. What this means is, okay, let's just read it together. You have a set of stable matchings. You take for each individual, and here we are assuming rural hospital theorem, so the same set of people are matched in all the same stable matchings, okay. Whether they are complete or not, it does not matter, just the same people are matched in every stable matching. They might have the same partner in some of the stable matchings, or they might have a completely distinct partner. Take each of their partners and sort them according to each of the agent's preference list. So we are going to generate the K-median stable matching. K-median basically means is that among these people for the so it's K-median from the man side, okay. So for each man you give, and that sorted list could be a multi-set because this man can have the same partner in multiple stable matchings. Either way you sort the multi-set, and then to each man you assign the kth person from this sorted list, okay. And to the woman you assign the L minus K plus first partner from their sorted list. Yes, it turns out this assignment that you have created is not only a matching, it is also a stable matching. Huh? Exactly. It's really not easy to see why such a thing should hold, right? Is it obvious to anybody? Why I just sort bunch of people, the same people might be appearing other people's preference list and their sorted list, and I just for all the men I give the kth person and all the women, how come the same woman is not the kth person in two man's preference list, two man's sorted list. If that happens, that itself would prevent it from being even a matching, right? This assignment would give the same woman to two men. And not only is not that the case, but it also turns out to be stable. And this follows from the proof that we just now saw. Yes, that interval proof. Just slight tweaking of that would allow us to.
K U is like K by L.
Very good.
K by L. So if that point we just assign.
Correct. It's not exactly K by L, but the intuition is very solid. K by L minus epsilon, slightly less than K by L. But that's the main thing. That if I could if you could somehow be close to K by L, I would be able to generate this. Okay, let's see. So basically what happens is the formal proof requires me to do something like this. I define this xij to be this summation of this p is this, that was m there, this is x, this is basically the pth matching, like I have L matching, right, m1 to mn. So this is the pth matching. In that, how much, whether I is matched to j or not, this would be 1 if I is matched to j in the pth matching, and it will be 0 otherwise, and I just add this up, okay. So if I and j are partners in more than one of those matchings, then this would basically be that number, the number of matchings in which it is a partner. And then I basically normalize by L, I divide by L. And then I know x is basically a fraction. So x is this vector consisting of these xij values. So x is a matrix, remember, it has like m x is a vector here, it's it's indexed by ij. So the ijth entry takes on this value. You can see that this is actually will satisfy the constraint of that polytope. That's easy, that should be easy to say, but okay. If you can't do that, let's assume it's true. Now you consider the case when I am uniformly sampling, it just so happens that it is very close to this quantity k by L. L is the number of matchings and k is the median that I want to hit upon, okay, where epsilon is a very small, arbitrary small value. Then every man is assigned to what? He is basically assigned to the k by Lth partner, right? Yes or no? There are L people and the k by Lth partner is literally the person who is ranked k in his ordered list. And by the coincidence property, we know this man should be this woman's k minus L plus 1 minus kth partner, right? It's just the other side, because the women were ordering their preference list from the other direction. The U falls in the exact same place for everybody, every row. It just that when we see from the women's side, if this is k by Lth for the man, it should, if it is the k among the L possible partners that they can have, from the women it should be L minus k plus 1. Okay, so that is why this basically gives that overlapping property allows us to say that, okay, if this is the kth partner for this woman is the kth partner of that man, then this man is that woman's L plus 1 minus kth partner. So basically that shows that theorem. Not any k, it's the kth median for which I want to find. Like I said, I want to find the kth median matching from the men's perspective, no? That k.
K is number from 1 to L.
Yes.
So when you said U is equal to K by L, are all the intervals of the length K? Why should all the intervals be of length K by L? And
I'm not saying that the intervals should be of length k by L, no? Why?
if it is possible that there are many intervals of different lengths, I don't see why k by n is chosen.
Okay, so let's draw this. So this is just saying this is this line. If this is, say, this is the value k by n, u falls right here. So notice the partners that I am seeing. So okay, so for every man I have the n possible partners are here on the interval, except the fact that all of them may not be his partner. At least some of them may not be his partner in among the L matchings that I have considered. Among the L matchings considered, there is only a subset of these n people who are their partners. Each of those correspond to a interval here. And because I have sorted them, I sorted the men's preference list, like it was a multi-set sort of a situation, and here also I sorted from the men's perspective. If somebody falls here, right, the L, there are only at most L intervals that are non-zero length. So if you does fall in one of the intervals, so it falls in one of those non-zero intervals, indicating one of the partners that belongs to this I in one of the L matchings. Correct? Okay. So now among that, okay, so notice something here. Xij is no longer the quantity of the fractional quantity of how much I am matching j. This is heavily biased towards people who get matched to I in multiple matchings. This is why this is xpij. This summation basically counts the number of matchings in which j and I are partnered together, right? So all these people, 1 to k people, the first, the people who are the men's preference list is, this is high portion. I guess the intuition here is the following, that among the L possible partners that he might have, among these L people, the first portion here, this part consists of people who are among the top k of his top k among those L partners, among those at most L partners. So exactly k by L, I had this. It's a good question.
So actually, if you do the complex computation, the first stable matching plus the second stable matching plus incidence vectors of all the stable matchings divided by the number of stable matchings.
Yes.
So in fact, you have the division of this line into L kind of long columns.
That's
Looking at the k column. So that is what you want.
Yeah, that's exactly what I'm trying to say. But how do we capture that the person who falls within this thing is exactly the kth median partner? It is at least k or better.
That is the definition of the kth median. So you look at each of the matchings in decreasing order.
Right, right.
Kth median is the partner you get.
Correct.
From a man's perspective, you get.
So if the same woman you get among the top, there might be just 2 of your partners, and one woman gets matched to you in k plus 1 stable matchings, and she is better than the other possible partner, then this person would be the kth median partner, right? That's a missing picture. So when I split the interval into L pieces, right, I am basically saying as if giving L distinct identities to those people, but bunch of them correspond to the exact same woman. So the kth point in the interval literally points to the person who comes kth in that list, and that's why it is the kth median partner. And that picture was completed. I was thinking, why is it not the kth person, right? So from the top, from the men's side, this is the first person who comes is the person he likes the most among the people, L people. Then comes the second person he likes the most. It could be the same person as the first one, if this person is matched to him in at least 2 or more matchings. Therefore, when I reach the kth interval, it is literally the woman who is his kth best ranked partner. Does that answer your question now? That's why we are, Okay, fine. Okay, then we'll talk later. Okay, I just have a few more slides. Okay, so the consequence of this is, okay, we obviously get back our some of the well-known results, which is that if L is equal to 3 and K is 1, you have literally a median property. That was conjectured by Conway in the 1960s, and this basically gave a proof of that. So these were all like, now when K is equal to 1, obviously we get back the man optimal matching. So why K equal to 1? That corresponds to literally the first interval among the L intervals 1 by Lth, that position. Okay, when L is the number of stable matchings and this is odd, then basically setting K to be this basically gives you the middlemost matching, middlemost stable matching. Is it clear? I think from the men's perspective, middlemost. So if you have the stable matching lattice, remember I said there is a man optimal matching and the woman optimal matching, and in that your basic, there is a weird matching which gives everybody, there is a stable matching that gives everybody their median partner among all stable partners that they can possibly have. Why should such a matching even exist is not actually clear to me, but it does, and this one captures that. So this, as far as I know, there is no combinatorial proof of this chain property. Do you know? Honestly, this is the only paper that is referred to. So this result would not exist if, at least from what we know so far, if it wasn't for this geometric perspective. Okay. So, okay, am I completely over time? Okay, I am just going to say one more sentence, and that's why it's a bunch of, and these are much more denser slides. So we have been talking about stable matching with rank preferences, right? Every individual comes with a preference ranking. We can have a slightly different setting, maybe a more well, it's not really general because one captures the other, which is called the utilitarian setting, where you assign, every individual gives a value to a potential partner. A high value means high desirability. So if I looked at the rank preference and say that the person who is sitting at the top position gets from me highest assignment, let's say the length of my preference list, right, and the second person gets n minus 1, n minus 2, then what you get is from the ordinal preference, the ordered preference list, you are inferring a utilitarian preference profile. And if you have a utility based preference profile, then you can also infer a preference ranking by basically sorting the people based on their utility values and so on and so forth, right. So they are, in this setting at least, they are somewhat equivalent. But here this is a very recent, the papers that I was talking about, Teo Sethuraman, is from 1998, the Rothblum and the Van der Watte papers are from the late 80s. This is from 3 years ago. So, you know, there's every sort of decade seems to have been represented in this talk at least. So this is a setting that was recently introduced by a bunch of authors whose name will appear somewhere else. So you have man, woman, and you basically have this utility value, and all the other constraint will look familiar. This is the matching constraint. This is saying mu is basically how much m would be assigned to W, and it should sum up among, for the woman W, this should be actually W is in this thing. Sorry, these indices are switched out, but the point is that every man can only be assigned to all the possible women, and the capacity cannot exceed 1. So this is the matching constraint and so on. So in this case also there is a notion of stability, which now takes into consideration the utility value. You don't just say I strictly prefer, you say, well, the utility I give to this person is higher than the utility I give to my current match partner. And in this world, we can have approximate notions of stability, something that you would not necessarily be able to do if you just had rank preference. So again, further forward, if we even more generalize the setting, going from like looking at things from a different perspective allows us to ask different questions and solve questions that otherwise may not be answered easily. Okay, so I think I am not going to, so this is another I would have walked you all through, but it is not that necessary. So this basically captures a notion of optimal stable matching, okay, that we would not know how to do or how to capture using Gale Shapley. See, here you have constraints, again there are polynomial number of constraints, right. So this can be solved, right, and you just have one objective function. And because again we are dealing with a stable matching polytope, the integral solutions are very well characterized. So what we need is to be able to solve this and infer the solution back in the integer setting. Okay, so I think I'll stop here. Thank you very much.
On behalf of IIT Jodhpur, I would like to present a small
Thank you, so beautiful.
So, I was not here. They want to click photo.
You would have known. Thank you.
Sorry, I was not here. I would like to invite
I saw that, but I didn't realize. It's very nice.